This is a GCSE chemistry tutorial within topic 5 on energy transfer in reactions. In this tutorial we will look at energy transfer, including exo and endothermic reactions, as well as looking at how to calculate bond energy. We will look at how to identify examples of exo and endothermic reactions. We will look at what is meant by exo and endothermic reactions, and we will have a look at how we would measure temperature change accurately. All chemical reactions involve a change in energy. This can either be an intake in energy or an output in energy. If a reaction releases energy into the environment, then it is an exothermic reaction. Exothermic reactions can be fast in the form of combustion, or they can be very slow in terms of rusting. Another example of an exothermic reaction is neutralization, the reaction between acids and alkalis, as these release lots of heat energy. Endothermic reactions, on the other hand, remove energy from the environment, so they take it in. This means that they feel cold. An example of this would be photosynthesis, which takes in light energy and therefore is taking energy in from the environment, making it endothermic. Another example would be the reaction between citric acid and sodium hydrogen carbonate, better known as bicarbonate of soda. This is the reaction that we find inside bath bombs as well as in sherbet. Another reaction that would be endothermic would be thermal decomposition, where heating a carbonate causes it to break down. As we are putting in the heat, this means that this is an endothermic reaction. You need to be able to explain how to test for energy transfer. This is a required practical for the AQA specification. The easiest way of doing this is to carry out a reaction inside a polystyrene cup. This is done because polystyrene cups are insulators. By doing this, we can accurately measure the temperature of the reagents before the reaction and compare them to the temperature of the product after the reaction. This will then tell us whether the temperature has increased or decreased, and we can work out the amount of energy that's been either gained or lost in the reaction. By using a polystyrene cup and putting it into a beaker full of cotton wool, we can make sure that we can reduce the amount of energy that's being lost or gained from the surroundings. We can also put a lid on to avoid any energy loss by evaporation. You also need to be able to look at reaction profiles or energy transfer graphs in order to work out if a reaction is exo or endothermic. In an exothermic reaction, the reactants, shown here, start off with more energy than the products have. They are at a higher energy level. This means that the energy must have been given out. The energy can't have just disappeared, energy can't be created or destroyed, therefore the energy must have been released. On a exothermic energy transfer graph, you'll notice we also have this period of activation energy. Activation energy is the energy required for the reaction to occur. Unless the reaction is spontaneous, activation energy must be added in order for the reaction to occur. This activation energy is the minimum amount of energy the reactants need to collide with each other successfully and therefore to react. The greater the activation energy, the more energy is required to start the reaction. This has to be supplied, so even for an exothermic reaction, we often need to add heat in order for the reaction to occur. This is most notable in combustion, where a piece of wood won't spontaneously combust with the oxygen in the air until we provide it with additional energy in the form of a spark or a flame. The energy transfer graph, or the reaction profile for an endothermic reaction, is the other way around. This time the reactants have less energy than the product, so energy is required to be put in order for this reaction to occur. This time we have a huge amount of activation energy required. We need to put in not only the energy that will be absorbed, but also the additional activation energy. So the activation energy is the entirety of this change. This blue arrow here represents the energy that's been absorbed and therefore the change in energy level between the reactants and the products. Energy is taken in, therefore the reaction is endothermic. We can also think about exo and endothermic reactions in terms of what is happening to the bonds. In an exothermic reaction, we are making bonds. The molecules are coming together and we are making bonds. In doing so, we release energy. For endothermic reactions, we are breaking bonds. This is because we are putting energy in order to split a molecule apart and therefore break the bonds between it. To look at this further, we're going to look at what we mean by bond energy calculations. This will look at the amount of energy that is either taken in or given out during the course of a reaction. Here we have a very simple reaction. The reaction is hydrogen gas and oxygen gas making water. In this we have two molecules of H2 with a single covalent bond between them, our HH covalent bond. We have one molecule of O2 with a double covalent bond, and then we have two molecules of H2O, both with two bonds of single covalent HO. To look at this, we need to think about which bonds need breaking. The bonds that need breaking in order to form our H2O will be this bond between the hydrogens and this bond between the oxygen. So we have got these two bonds and this double bond that need breaking before we can form our new bonds. This means that we can calculate the amount of energy that needs to be taken in order for these bonds to break. Therefore, we can look at the endothermic part of this reaction. The good news is that in your GCSEs you will be given the bond energy values. You may be given additional bond energy values that you do not need in order to complete the calculation. In order to work out the energy taken in, we need to work out the amount of energy required to break our two hydrogen-hydrogen bonds and the amount of energy taken in to break our oxygen-oxygen bond. As we have got the bond energies here, we can easily calculate this. So we will do 2 times 436 and then add it to 498 in order to work out the energy taken in on the left-hand side of the reaction. So this gives us 436 plus 436 plus 498, giving us a value of 1,370 kilojoules per mole of energy taken in on the left-hand side. As we can see, we have now successfully broken our 3 bonds. As we now have our energy taken in for breaking bonds, we need to now work out the amount of energy that will be released as we make the bonds on the right hand side. This will be the exothermic part of the reaction. I want you to pause the video and work out how much energy is required in order to make these bonds. So in order to do this, we need to work out our amount of energy. As we have got 4 hydrogen to oxygen single bonds, we need to do 4 times 464 kilojoules per mole, or 464 plus 464 plus 464 plus 464. By doing this, we get a value of 1,856 kilojoules per mole of energy that will be released in this reaction. We now have 2 values. We have a value for the energy taken in during the reaction and a value for the energy released during the reaction, which means we need to calculate something known as delta H. At A level, this will be known as the change in enthalpy. or, for GCSE, the change in energy. Delta H, our change in enthalpy or our change in energy, is equal to the energy taken in during a reaction minus the energy released in the reaction. So for our reaction for making water, we will do 1,370 kilojoules per mole, take away 1,856 kilojoules per mole. This gives us a value of minus 486 kilojoules per mole. As we looked at earlier in this tutorial, we can then relate this back to our energy transfer graphs or our reaction profiles. Remembering the products of an exothermic reaction have less energy than the reactants. The spare energy, that lost energy, has gone into the surroundings. Because of this decrease in levels of energy, this means that the change in enthalpy, the change in energy, will be negative. So, if you get a negative value for your delta H calculation, this means that it is an exothermic reaction. If delta H is positive, it will mean it is an endothermic reaction. So, to practice this, here is another question. I want to calculate the energy change when nitrogen bonds with hydrogen to make ammonia. And I want you to calculate if the reaction is exo or endothermic. You've been given 3 different bond energy values, and to help you out, the calculation is as follows. Our balanced equation is 3H2 plus N2 goes to 2NH3. For those of you doing triple science, this equation will be of particular relevance as this is the equation found in the Haber process. I want you to pause the video now and attempt this question. So, for your answer, you should have found that in order to break the bonds in the reactants, those 3H2 and the N2, you had a value of 2,253 kilojoules per mole. In order to form the bonds in the products, the ammonia, we should have found that you had 2,346 kilojoules per mole. To work out your energy change, your delta H, you do your energy taken in minus your energy released. This will be 2,253 minus 2,346, which is equal to minus 93 kilojoules per mole. So is this exo or endothermic? Well, as it is a negative value, this reaction is exothermic. We can go further by explaining how exothermic it is. Minus 93 is quite a small number, therefore this would be a slightly exothermic reaction. If we compare it to the value we found for the formation of water, which was a much larger negative number, then the reaction to form ammonia is less exothermic than the reaction to form water. In the next video, we will look at fuel cells as well as how to make battery cells.